Welcome back, everyone. Last week we stopped with a short discussion of the simplex algorithm by Nelder and Mead. I wanted to give you a small recap of what we discussed and what this algorithm is actually all about. The basic idea is that you have a list of possible solutions for your problem and you identify the worst solution, you eliminate the worst solution, and then you come up with a fancy idea of constructing a new potential solution, and you test whether this is an improvement. If it's a very large improvement, you take a step even further in the direction of this improvement. If it's not an improvement, if actually the new solution is worse, then you take a step back and you move in the opposite direction of where you've just gone. And this is shown here on the next slide. You remember in the two-dimensional plane what I showed you here. Remember that you're trying in this setting, you're trying to optimize a function of two variables, x1 and x2, and this is x1 and this is x2. This plane, this graph, does not give you any hint whether this point or this point is optimal. For this to work, obviously, you would need a three-dimensional plot in x1, x2, and y. Then, if you were to plot a function mountain, Funktionsgebirge, then you would see where the optimal point is, if there is one. But here, we only look at the potential solutions with parameters, with coordinates x1 and x2. So this point here, or this point here, these could be, any one of these could be the optimal point. The idea is now that, like I've shown you here, that you take, let's do this again, that you take the potential solutions, and there will be more than two or three, obviously, but let me just erase all this. You take a point here, and maybe here, and here, and here, and here. If you link all these points as part of a simplex, then this would look like this. Okay. Now assume that this point here gives you the worst value for y. So if we are minimizing the function, this could be the point where the function takes its highest value. Then the idea is now to eliminate this point. No? Okay. Usually if okay, now I've got the eraser. We eliminate this point, we combine the remaining points, and actually the original point was here, and then we have the point of gravity of the remaining points, that is here, and then one could think about mirroring this point here to this point. And then we have a new point here. This one's eliminated. And we try out this point and calculate the function value for this point. And again, in the algorithm, this is described in pseudocode. As you can see, it is a little bit more complicated in the sense that the algorithm is tuned to make sure that if you are moving in the correct direction of a better solution, you go a step further. If you see that you're not improving on your set of potential solutions, you go one step back. And in two dimensions, this would mean here that instead of going, for example, from a point here, this would mean that instead you move into the other direction. And you do this in each and every iteration until the algorithm converges, or you reach a maximum number of iterations. So this is a very simple, or it's not a simple algorithm, but it's the idea is quite simple. By the way, this general idea of having a set of potential solutions, eliminating some, improving on the list of solutions, and inserting some new solutions, is also the framework for for heuristic algorithms, like, for example, genetic algorithms and some other types of heuristic algorithms. Genetic algorithms are what? Genetic algorithms take up the idea of genetics and biology, that you have a population. You try to produce new elements to your population, and it's like in genetics, new combinations of two members of the population. If they are an improvement, they will survive. If they are no improvement, they will die out of the population. And genetic algorithms have the same idea, and they mimic this mathematically, that you have a population of solutions, and you combine solutions, produce new solutions, and eliminate others that are not as optimal as some other points. Those are genetic algorithms. Same with in heuristic optimization, you have many ideas coming from other fields. Like there's one algorithm called harmony search. Harmony search is an optimizer that takes up ideas from orchestras that try to find the perfect harmony of instruments. Then you have simulated annealing. Simulated annealing is the process when producing steel of slowly decreasing the temperature in a glowing piece of steel as to prevent cracks. If you were, for example, to take a piece of steel that is melting hot, and if you were to throw it into cold water, the sudden decrease in temperature would produce cracks in the steel. And annealing in engineering, you use the process of annealing, of slowly decreasing the temperature. And simulated annealing is a famous optimizer, an optimization algorithm that simulates this process of slowly decreasing the temperature. And then, of course, you have ant colony algorithms that take up their idea from ant colonies. Okay. Now let's turn to optimization in MATLAB. How is it done in MATLAB? We consider a very simple problem of minimizing a function in two variables, x1 and x2, x1 minus 2 to the fourth power plus x1 minus 2x2 squared. Very simple. Obviously, we can see that because we have two expressions here, squared and to the fourth power, that obviously the function is non-negative. And if it's non-negative, the best function value for a minimization is 0. And we can immediately see that for x1, 2, and for x2 being 1, this becomes 0, and this is the optimal point. This is the minimal point. Clear, everyone? Function needs to be non-negative. And for 2, 1, this point here, we get the 0, so that's the optimum. Now the gradient is given by, if we calculate the gradient, we get this here, this vector. We can see that in this point 2 and 1, the gradient becomes 0. And in MATLAB, we can use fmin search or fmin unc. Fmin search is a variant of the simplex algorithm, and fmin unc is a set of various algorithms that, depending on what you're trying to optimize, will switch from one algorithm to another. We apply both algorithms, and you can see with fmin search, we'll get the result 2 and 1 up to 15 or 16 decimal points. And the function value f of x is 3 times 10 to minus 17th power, so almost close to 0. That's okay. F min unc, same problem, different algorithm. You can see that x is now 1.9897 and x2 is 0.9948, and the function value is again close to 0, but it is only close to 0, 10 decimal points worse than the result for f-min search. Now, why is this the case? We'll see on the next couple of slides that obviously this is related to the fact that f-min search uses a variant of the Nelder-Mead algorithm, and f-min unc is a gradient-based method. And something seems to be off with the gradient method here. So we have a slightly worse result for f-min unc than with f-min search. The reason for this is that the target function is relatively flat at the optimum, meaning that also the gradient will be close to 0, and this makes it harder for the gradient-based method to find the optimum. To improve on this, because we know analytically the gradient of the function, we can supply MATLAB with a gradient. If you look up the documentation of f-min unc, you will see that MATLAB tells you by default f-min unc chooses the large-scale algorithm if you supplies, that's a typo in the original documentation, the gradient in fun, and the grad object option is set to on using optim set. This algorithm is a subspace trust region method and is based on the interior reflective Newton method. We've only seen the basic Newton method, but it's an extension of the Newton method. F-min unc with a large scale option set to off with optim set uses the BFGS quasi-Newton method. You will probably never see this in a lecture. Most of the optimization algorithms in MATLAB are also, I think, Starter. They use some variant of the BFGS algorithm. A couple of years ago, I still remembered what BFGS stands for. I only know, I think, Goldfarb and Channel. Those are the last two words. Those are it's an abbreviation for the 4 authors on the paper that proposed this algorithm. Now let's use f-min unc, but we'll supply the analytical gradient. So we'll write f, that's our target function, our objective function. Grad f is the gradient. As you can see, 4x1 minus 2 to the third power plus 2 times x1 minus 2x2 minus 4 times x1 minus 2x2. We'll set the options to on here. And now we need to call f-min unc using not just f, but also grad f. And we'll start again with the solution in 0, 0. Now, as you can see, now if you supply the analytical gradient, the initial solution is improved by almost 7 decimal points. Why? Because what is different now, if we do not supply the analytical gradient, MATLAB will use an approximation to the gradient. This is something very interesting. When I started with my PhD, and I was still studying mathematics, at some point I wondered why you will find a lot of numerical analytical tools to approximate an integral. An integral, this is actually quite interesting. There is a huge literature on quadrature. In German, Quadratur. The word quadratur, in German Quadratur, is numerical integration, finding an approximation, a numerical approximation to an integral. Now with integrals, this is quite difficult. Sometimes you have a function like this, and you need to find this space below the function here, and you might know this from school. There are some simple examples and some simple ideas how to approximate this space, but it gets more difficult with f becoming more nonlinear and becoming more complicated. With numerical differentiation, the numerical approximation of a derivative, you will not find too many methods. Why? Well, remember what a derivative is. In any case, if your function looks like this, and you need the derivative at this point, well, what is a derivative? Well, the most basic approximation is simply take the tangent line. And that's not a too demanding task for a computer. So what will MATLAB do? MATLAB will take the function and it will take, in the simplest way, it will take 2 points here and here. It will construct a triangle and use a triangular approximation to the function at this point to approximate for the derivative. And this is what MATLAB does in fmin_unc by default. It will approximate the derivative because we are not supplied with the analytical gradient here. If we do this, you can see that in this case, the numerical approximation MATLAB does automatically is actually not a pretty good one. And if we supply MATLAB with the analytical gradient, we can improve on the accuracy of this solution. However, obviously, if we are mistaken, if we miscalculated our analytical gradient, the result will obviously be worse. And we can check for this by also using the option derivative check. We are now setting the option derivative check to on, meaning that MATLAB compares its own analytical approximation with the analytical supplied derivative supplied by the user. And if it sees that its own numerical approximation is far off and quite different from the analytical derivative, it will give out a warning. Otherwise, we are fine. So to do this, we are now using grad f1 that is not exactly the analytical gradient. There, one parameter, one coefficient is slightly different. As you can see here, we have a 4, that's correct, and here it's the same, but this is a 6. So we miscalculated the analytical gradient. In other words, we were too stupid to calculate the first derivative of the function. To see this now, and if we are using grad f1, you will see that MATLAB checks for the accuracy of our analytical gradient. If it checks out with the numerical approximation, it gives us a warning: maximum discrepancy between derivatives. Warning: derivatives do not match within tolerance. Derivative from finite difference calculation -32. User supplied derivative -48.0. Difference is -16. And the result is, as you can see, we can still continue with the optimization, but you can see again the result is slightly off. So it's again back to the numerical approximation. That's what you can do in MATLAB. You can use fmin search, you can use fmin_unc. It depends on how good your knowledge of the curvature of the function is, and if you want to rely on a gradient-based method. If you think that the function is relatively flat and it's difficult to approximate for the gradient, then you should use fmin search. Otherwise, fmin_unc will give you a better result. Okay. Now, this is unconstrained optimization, meaning that you have a function and your variables can range between minus and plus infinity. Now we want to include constraints. We will have constraint optimization, And this makes life much, much more difficult. Why? In one dimension, it is quite clear to see this. If this is the function, we can see that this is the maximal point. This is probably, this is a local minimum. Let's leave it at that. And let's assume that the function continues to look like this. Then this would be a local minimum. This is the global minimum. This is the global optimum. And we know from school, take the first derivative, set it to 0, and you can calculate all the potential optima of this function. We don't even need MATLAB for this. But as soon as we introduce constraints, saying, for example, x has to be larger than 1, and if this is 1, then suddenly we have a constraint that will cause the optimization to only look at this area. And now suddenly this point is out of the picture. And we still have one global minimum, we have one global optimum, but what could also happen? If we were now to say that, say, we have a second constraint, and say that x should be smaller than 4, then suddenly our global minimum does not satisfy the second constraint, and our previous necessary condition that the gradient or the first derivative has to be equal to 0 cannot be fulfilled by this global minimum, which is now a function value where you still have a non-zero first derivative, where the gradient is non-zero. So everything we knew before with the gradient-based methods, that you should check for potential solutions where the first derivative or the gradient of the function becomes 0, that necessary condition is no longer necessary. It might be that your global minimum or maximum is exactly at the edge of your solution space, where the solution space is cut off by one of the constraints. So this is the problem with constraint optimization, and we can try to include this by first using so-called penalty approach and penalty function approaches. Now we'll discuss procedures for optimization under constraints. We'll consider optimization of a function f of x. X is a vector. We want to minimize f subject to two sets of constraints. First of all, we'll have functions hi that have to be equal to 0, or we have constraints in the form of an inequality of functions gi that are smaller or equal to 0. First, you need to note that every constraint can be converted to yada 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 equal or smaller or equal to 0. We don't need equal to 5, smaller than 5, or 17. You can just bring it to the left-hand side of the equation or inequality or inequation, and then you'll have this form. And it matters whether it's an equation or inequation. Now we assume that the corresponding objective function has the required differentiability properties, but even differentiability doesn't assure that the gradient vanishing, becoming 0, is a necessary condition for an optimal point. So that's no longer a necessary condition. The solution will most likely be on the edge of the solution space, and we can solve this, or we can try to solve this, by using a penalty function approach. You can also derive more general stationarity conditions. In mathematics, you will learn about the Kharash-Kuhn-Tucker, the KKT conditions. That's a generalization of more or less the Lagrange approach. But in the special case, where you have certain conditions and constraints and a certain function, the Kharash-Kuhn-Tucker conditions will give you the same result as the Lagrange approach. But Kharash-Kuhn-Tucker is much more general, but it's much more complicated. So I'll leave this out. Last year, and if you look at the German slides, last year I still had this in this lecture, but I think this is too complicated in retrospect for economics students. Now, what is the penalty function approach? It's a very simple idea. You loosen the constraints by incorporating them into the target function. So what are you doing? You take the minimization problem, minimize f, unter den Nebenbedingungen such that hi of x is equal to 0, and you transform this into a different function, phi of x and sigma, and you create this new objective function by writing f of x plus sigma, the sum of the squared constraint functions hi of x. Now, what happens now? We want to minimize not f, but phi. These constraints, ideally, if x fulfills all constraints, h1 of x will be 0, h2 of x will be 0, and so on. If we square it, we'll have 0. If you summarize it, if you sum it up, will also be 0. And if all the constraints are fulfilled, phi will be equal to f. It will be equal. If any one of these constraints is violated, phi will be larger and will give a function value that is larger than f. And in this case, if we optimize over x and sigma, we'll choose the right combination of x and sigma so that the result will be minimal in the sense that f is minimized, and optimal in the sense that ideally all constraints are fulfilled and are respected. What are we doing with the parameter sigma? Sigma is the parameter that punishes a violation of any of these constraints, and will increase sigma as to tell the algorithm you should start to find solutions that fulfill all constraints. If we were to set sigma equal to 10,000, this would mean that the optimization can be done simply by fulfilling all constraints. And then you need to, if all the constraints are fulfilled, then you need to look for the optimal x. So in the end, it's again a different function, but you're punishing a violation of the constraints. Okay. Similarly, you can use the same idea to include now constraints in inequation form. So you minimize phi equal to f plus sigma times the positive or the negative part of the inequation. That's here and here, or you can also square it. And in all cases, one will use increasing values of sigma. So at the start, it might be that some of the equations or inequations are still violated, but as you move along from iteration to iteration, you will tell the algorithm by increasing sigma that it now has to start caring about the constraints. And all three approaches, they describe so-called exterior penalty function approaches at which the permissible solution space is approximated from outside of the solution space. Now, you have to think about this like this. This is the solution space. This is the permissible solution space. And this is the space that would be possible and admissible if we had no constraints. And it's an exterior penalty function approach because you allow the algorithms to start somewhere where one or more of the constraints are still violated. And this is, if you then increase sigma, perhaps you'll start at a point like this. Simplest case is if sigma is 0. If sigma is 0, you don't care about the constraints at all. And then you will start somewhere where f is optimal without constraint. And this could be the case, and by increasing sigma, you will force the algorithm to move into the solution space, respecting the constraints, from outside of the solution space. Now, if the optimal solution lies on the edge of the permissible solution space, then with an exterior penalty function approach, the optimal solution is only found in the limit. And if this is undesirable, you can use an interior penalty function approach. And with these methods, a suitable threshold function, a so-called barrier function, is introduced, which strives towards infinity if x strives towards the edge of the admissible solution space. So one example of this is this function b of x that is minus the sum of 1 over all those constraints in inequation form, and then you optimize f of x plus sigma times b for decreasing values of sigma. Other idea, you are using a starting point in the solution space and you are loosening the constraints and you're moving from the inside to the outside of the solution space, at which point you will stop. And then, if the expression is small enough, you abort the algorithm. So let's look at one example. We minimize f of x equal to x minus 1.5 squared plus y minus 0.5 squared under the condition that x and y are smaller or equal to 1. Now again, we can see the optimal solution. Optimal solution is given by x star equal to 1 and y star equal to 0.5. Again, same idea. You have two squared expressions, so f will always be non-negative, so the minimal function value is 0, and this becomes 0 for 1 and 0.1. Again, obviously, if now it would become 0 if we were to use this. Now, remember, x needs to be smaller or equal to 1, so the optimal x value in this constraint optimization is 1 and not 1.5. An interior penalty function could, for example, be, now, this is the function. Oh, no, that's not f. Let's call it, what do we call it? Phi. X minus 1.5 squared plus y minus 0.5 squared plus sigma over 1 minus x plus sigma over 1 minus y. And we'll visualize this in MATLAB. F is the function, y, x and y is now a mesh grid. I showed you how you can generate vectors in MATLAB. Now here I'm creating a discrete grid of 2 dimensions, x and y, by starting at 0.01 and going up until 0.99. And I'm plotting different subplots now for, and as you can see, this is a function in sigma, x and y, for 0.1, 0.01, 0.001, and 0.0001. Those are the sigma values, and sigma is decreasing. And this is the result. Remember, where is the optimal point? The optimal point is 1 and 0.5. So in this case, will be here. And I'm plotting the function mountains. So this is 0, 1, 0, 1. So this here is the point 1, 0.5. Yeah? And in this plot, you can see for different sigmas, sigma 1, sigma 2, sigma 3, sigma 4, the function graphs. And as you can see here, it seems that with a small sigma, or actually a very large sigma in contrast, one would think that the optimal point is here. Then you can see that the optimal point would be here, then it's probably here, and then hopefully it's here. So it moves into the direction of the solution we are looking for, and it's forced from inside of the solution space to the edge. Yeah? So that's a penalty function approach. And it's comparatively simple. And there are some problems that can occur with such an approach. So this is usually a very good start, but one should use more sophisticated methods to try to find different solutions and then check which solution is better. That's, by the way, one very good thing about optimization. If you have two algorithms at your disposal, if you find two very distinct solutions, you can enter those solutions into the function. And if you see that if f of x1 gives you 0.05 and the second algorithm gives you a solution with a function value of 0.002 and you want to minimize, then obviously this algorithm has yielded a better result. You can always check for the optimality and the superiority of your algorithm when it comes to function minimization. Okay. Now let's do this in MATLAB. In MATLAB you have different methods at your disposal for linear programming, for quadratic programming, and quadratic optimization, and a generic optimizer. You have linproc, quadproc, and fmin-con, in contrast to fmin-unc for unconstrained optimization. So let's look at all these functions. You can use linproc. We want to maximize f of x, x1 plus x2 with respect to g1 equal to x1 plus x2 is smaller or equal to 1, and x1 and x2 are non-negative. So the program possesses two basis solutions. Let me get back to linear programming to give you some background in linear programming. Linear programming and linear optimization means your target function is linear, affine linear, and all the constraints are linear. Which means that you will have, in 2 dimensions, you will have a solution space, and what will happen now is, for example, that with all those linear constraints, you will, in the end, get a simplex as a solution space. Let me just include one other. Assume this is linear. Then, what is the solution space? This area here. And it's simple to see that the solution space is a simplex. If you remember, what is a simplex? In German ein konvexer Polyeder, also ein Polyeder, I don't know whether the same word exists in English. Konvexer Polyeder ist also ein konvexes Vieleck. Im Gegensatz zum Rechteck, zum Viereck etc. Das ist also die Verallgemeinerung und konvex, das ist ein Simplex. Now, the nice thing in linear programming is your target function can also be included in this graph, and you start, for example, here at the 0, and then optimization is done by pushing out your target function linearly in parallel to the most outer point of your solution space, and this is probably this point here. Let's assume this is all parallel. Then here, at this corner of the simplex, you have your optimal point. It's somehow the same idea whether you remember indifference curves in microeconomics. You also have your constraints, and then you have your indifference curve, and by pushing out your indifference curve, you are getting to higher utility levels. Same here. You take the first one, and then you have to shift it in parallel away from the 0, and then this is the optimal point. This in linear programming, you will see that life is actually very simple in these simple examples, because you only need to check for the solutions at the corners of the simplex. And then there are three potential solutions. First, two constraints are disjoint. They cannot be fulfilled at the same time, so the solution set is empty. Second possibility is you have a simplex that looks like this, and your target function touches the simplex at one of the corners. Then you have one solution, and the third case actually is if you have a target function that touches one of the sidebars of the simplex. Then you have an optimal solution here and an optimal solution here, and any convex combination of these points here is also a solution. So, meaning you have infinite solutions, and each and every one is just as good as the other. Linear programming, linear optimization is simple when it comes to these cases of small numbers of equations, inequations, and variables. And in this case, you can see that, you need to prove this, you have infinite solutions. You have two basis solutions, 1, 0 and 0, 1, and all combinations, all convex linear combinations between 1, 0 and 0, 1, all these are optimal. So the function call is now x is linproc of f, a, b, a equation, b equation, lower bound, upper bound, starting value, and options for minimizing f. And we now do this. We do linproc, -1, -1, 1, 1, 1, and so on. And we minimize this. Again, remember, we want to maximize this, so we need to change the maximization into a minimization problem. That's why we now have -1 and -1 here. And as you can see, MATLAB gives you a solution 0.5, 0.5. This is different from the two solutions I gave you. Well, what MATLAB does is it finds one solution that is optimal. And it seems to be that we have a point 1, 0 and a point 0.1. All the solutions between those 2 points on a linear line are optimal, and it gives you this one, 0.5, 0.5. So yes, this is an optimal solution. Unfortunately, MATLAB does not tell you that this is not the unique solution. it's one of infinite solutions. But it's still optimal. If you set the options slightly different, you will get one of the basis solutions. Okay. Now let's turn to F-min-con. We solve a slightly more complex function minimization. We minimize the exponential function of x1 times and so on with respect to g1 equal to x1, x2 minus x1 minus x2 smaller or equal than 1.5 and x1 times x2 larger than 10. Now for MATLAB, it's only a question to change all this into the form that MATLAB expects all those functions and constraints. We have F-min-con function, starting value A, B, A equation, B equation, lower bound, upper bound, meaning that A and B, those are the functions for the constraints in inequation form. These are the equation form, and we have a lower bound and an upper bound for x, and some options. So let's do this. Function conf1. These are the nonlinear constraints in inequation form. 1.5 plus x1 times x2 and so on. We also have the nonlinear constraints in equation form. C equal is 0. We need the objective function. Very simple. And then we'll set the options. We'll have a starting value -1 and 1. And again, we need to supply F-min-con with all these arguments at objective function x0. And here, those are the constraints we want F-min-con to respect. It'll use a different algorithm and optimization terminated. First order optimality measure less than options tolerance function, and maximum constraint violation is less than options.tol.con. Active inequalities to within options in equation nonlinear 1 and 0, function value fval and optimal x 10.5523, 0.9477. This is the result. Question is, how good is this result? You would need to use different algorithms and to check whether this is really the optimal value with these constraints. Okay. Any questions concerning the optimizing algorithms in MATLAB? Again, to fully understand what MATLAB does, one would need to read through all the documentation of these functions. F-min-con, F-min-anc, F-min-search, these are highly tuned algorithms that will switch from one algorithm to another if it detects that the problem is not, or the algorithm is not suitable for this type of problem. It will check the derivatives and so on. And it's just important to note how to use these functions and what could go wrong, and to definitely use more than one algorithm to see whether you can improve on your result. Now, let's do a small example with portfolio optimization in practice. Let's take all these algorithms and see what happens if we were to use real data and the functions in MATLAB. Now, in this part, we want to exemplify portfolio theory by Markowitz, the efficiency line. To this end, mu is the vector of expected returns. Sigma is again the vector of standard deviations. C is the symmetrical variance-covariance matrix of n securities. W defines the vector of portfolio weights, where Wi is the portfolio weight of asset I, and the portfolio weights add up to 1. A portfolio weight Wi smaller than 0 corresponds to a short sale. And with a fixed weight W bar, the expected portfolio return is mu p bar, and the standard variation, the variance, not the standard variation, the variance is sigma p squared. Okay. Let's start with the Markowitz optimization. We want to exemplify the efficiency of some portfolios by minimizing portfolio variance such that we have a constant expected portfolio return and the weights all add up to 1. Now with the Lagrangian approach, we get a function f, half weight vector transpose times covariance matrix times weight vector minus nu, and so on and so on. And we need to minimize this to solve for this optimization. You know that you need to take the first derivative with respect to all those variables, x, or in this case w, the weights, and the Lagrange parameter. Set all those to 0, solve for w, and this is some simple algebra now. You get the formulas for the portfolio return, and you get this. You can substitute this expression with a, b, b again, and d. Now, then this is a solution of a system of linear equations with a, b, and d times nu and lambda equal to the portfolio expected return and 1. Now, this means we get this. You can calculate this at home. And in the special case of a equal to b equal to 0, we get a minimum portfolio variance without any constraint on the portfolio return. So in essence, we get the minimum variance portfolio. So if we then insert this, equation 2 simplifies to 1 equal to weighting vector times 1 is equal to, and so on, meaning lambda is 1 over d. If we insert this, we get the weight vector for the minimum variance portfolio. We've seen this a couple of weeks ago in the two asset and the two stock case. Now this is the general formula. No? This is simply the optimization. It's quite simple. If you only have two stocks, then you have one, and you get the additional constraint that you put A into stock 1 and 1 minus A into stock B, stock 2. And then you have a one-dimensional function, you minimize it, and you get the optimal x, the optimal share of stock 1 in the minimum variance portfolio. This is the same result just in the n-security case. So the weight vector is 1 over d times the inverse of the covariance matrix times the transpose 1 vector. Okay. If we insert this into the formula of the portfolio variance, portfolio return, you get the expected return and variance of the minimum variance portfolio. Inserting this into the general equation leads to the equation of all risk-efficient portfolios. So expected return of any efficient portfolio has to equal the return on the minimum variance portfolio plus minus the square root of this expression here. Now let's take all of this to the data. We look at share prices of 7 companies from the German DAX between September 2001 and March 2016. We take Adidas, Deutsche Bank, Deutsche Post, RWE, Siemens, ThyssenKrupp und VW, more or less as it's the DAX blue chip companies. Source of the data is Yahoo Finance. I have to stress this. In the empirical banking class in our bachelor's degree, I teach each and every one of you, never ever use Yahoo Finance in your bachelor or master's degree thesis. Why? I compare this in my script with tennis. Of course, you can use a low-budget 10-euro racket in tennis, but you would never start at Wimbledon with such a low-price tennis racket. You know? Professionals use professional tools, and Yahoo Finance is something that is nice for a quick look at a plot, but if you were to use this data in a professional context and a master's degree and a master's thesis in empirical analysis and research is a professional context, you would use DataStream, Bloomberg, Compustat, or some other professional tool that is not publicly available, but that it's proprietary. These are the closing prices from the Frankfurt Stock Exchange, adjusted for dividends and splits. But for our purpose, because I want you to test this at home, I wanted to use publicly available data, and for this purpose it's okay. These are the stock prices. And as you can see, well, what can you see? You see September 11, the crisis after the attacks on the World Trade Center. You see the boom cycle until the financial crisis. You see the financial crisis, and you see the increase and in stock prices and the boom again after the financial crisis and after central banks started quantitative easing. What is this here? That's the diesel scandal of Volkswagen. You can see that the stock price of Volkswagen decreased dramatically as a result of the diesel scandal. Okay. So these are the stock prices. And now let's turn to MATLAB. M is the number of days, N is the number of stocks. It's always a good start after having uploaded the data to MATLAB or any computer system, to R or Stata or Mathematica. It's always good to extract the dimensions of your data array. N is size of price. After having inserted the data as an array price in MATLAB, you get the number of days and the number of rows and the number of columns. Then we'll start with a zero matrix return for the daily log returns. We calculate the log returns. You can do this in MATLAB or you can use Excel for this. I usually download the data to Excel, compute the log returns in Excel, and then upload and import the log returns in MATLAB and R. So for I equal to 1 up until m minus 1, return I is the log of price I plus 1 minus the log of price I. Again, remember the log return is the difference of two adjacent prices. Then we want the return, so we calculate return equal to return times 100. You might know this from any programming class you have taken. If ever you see something like this, this means that you take the variable a, you increase it by 1, and you update a by the new result. If you write a equal to a plus 5, this would mean that now a is, let's say, 12, and in the program after this a is 17. That's what meant by return equal to return times 100. If you've never used a programming language, if you've never coded a program, this might look weird to you, but I hope that you've already used C, C++, or Java, right? Okay. Now the returns, they are cleaned with respect to extreme outliers. We assume that any observation, any return that is smaller than minus 20% or larger than 20% is considered an outlier. You can do this. It sometimes makes sense to exclude outliers. Sometimes it doesn't if you are trying to model outliers and extreme returns. Now, for simplicity, I excluded outliers, meaning that you can do two things with outliers. You can simply leave them out. You can set them to 0. That wouldn't make sense to me. Or you can do something that is called Winsorization. What is Winsorization? If, for example, you have observations that look like this. And you agree that you are cutting off at plus minus 20%. Then maybe this would be plus 20%, this would be minus 20%, then obviously this here is an outlier. And you move this to this point, and then it's called winsorized, winsorisiert in German. Yeah, you're not excluding it, but you're changing the value of the observation to the threshold you used for winsorization. Okay. So we now check for outliers, identify the days on which an outlier occurs, index for I equal to 1 to n, index is index, find return larger than 20 or return smaller than minus 20. Delete double entries and then return the vector of returns, the matrix of returns, without the outliers. Okay. In this case, 4 days out of the 3,722, these are outliers. Mm-hmm.
One question regarding the outliers. Why should I keep these outliers and winsorize them? Because I would think that this is some kind of data manipulation, isn't it?
It's always, yeah. In this context, one usually does not do outlier exclusion and winsorization. You do it frequently in regression analyses. Because if you have a panel data structure or a cross-sectional data set, let's assume I want, very simple example, I ask people running around on the street for their age and their income. And I want to show that age or income increases with age. The older you are, the higher your income is. Now suddenly someone comes by who is 5 years old and someone comes by who is 115 years old, 2 outliers. If I do a regression analysis, ordinary least squares regression is sensitive to outliers. So it could be that these 2 extreme outliers drive the results and they lead to a bias of your regression analysis, even though those are only 2 out of, say, 1,000 observations. And to minimize this bias, you do winsorization of the independent variables, of your explanatory variables. Even better example, you want to study firms and you include Deutsche Bank and you have total assets as an explanatory variable. If you take the DAX companies, Deutsche Bank as a bank will have an extremely higher total assets, an extremely larger balance sheet than any other company in the DAX. So results will be biased by the fact that this is an outlier. So what you do is you take all the values of your explanatory variable in the cross-section of the panel and you usually winsorize at the 1 and 99% quantile. So you don't take an absolute threshold, 20 minus 20%, but you use a relative threshold, and that is done with the 1 and 99% quantile. But this is more relevant in regression analysis. In these scenarios, where I'm using stock returns, usually I'm very interested in these extreme returns because they are the black swan events I'm trying to find. But you're right, if I'm only interested in stock returns, one should probably not exclude outliers or winsorize them. Okay. Now we calculate the required parameters and the market factors. Mu, covariance matrix, as well as the inverse of the covariance matrix. Mu is simply mean of return. C is COV of return, that will give you the covariance matrix. And the function INV, inverse of C, gives you the inverse of the matrix C. So this is very simple in MATLAB. And this gives you mu, sigma squared, the covariances, and the inverse of the covariance matrix. We can also calculate those parameters A, B, and D from before. A, B, and D. Very simple. Those are these Markowitz parameters. Then we can calculate the weights of the minimum variance portfolio. So W varmin is 1 over D times C1, the inverse of C, times a vector of 1s. And you can see here the weights of the minimum variance portfolio. And the corresponding return and standard deviation are sigma min and mu min, 1 over square root of D or B over D, sigmap, and we now calculate the efficient frontier, sigmap, sigma min from 0.001 to 4, and these are just mu p1 and mu p4, and you can see this, I've already highlighted the efficient and inefficient portfolios in green and blue here. And you might remember that so far we've only seen theoretical examples, stylized plots of what the efficient frontier looks like. This here is mu sigma plot based on real data. Now using these, I think, 8 assets, you can see that this here, this is the efficient frontier of portfolios out of any of these 8 assets that is created by this financial markets. These are again inefficient, but it really does look like an eggshell. Okay. So this is the efficient frontier. Now, an interesting idea now is we go back to naive diversification. We now think I'm smarter than everyone else. I don't use Markowitz optimization. I simply use a random portfolio with random weights. As long as I diversify randomly, I will be off quite well. So what I do is I take 2,000 random weight vectors, I calculate the resulting portfolios, and I plot them, and this needs a little bit of some experience with for loops in MATLAB to get the random numbers, but let's now plot this, and as you can see, most of the random portfolios are not just inefficient, they are not on the efficient line, they're actually also in the lower border, the lower half of this eggshell. Yeah? This is where most of these random portfolios are. So naive diversification in the sense that you simply choose a random weight vector will cause your portfolio to be highly inefficient. Now, let's go back to this. This gives you rent 1. The way to do this is what? If I have 5 parameters, 5 assets, I choose the first one, the first weight as a random number between 0 and 1. I check whether I've already chosen a number that brings the sum of all weights larger than 1. And if that is still the case, if the sum of all weights is still below 1, I generate a new random number for the next weight. And at some point I stop and I set all the remaining weights to 0. Yeah? So I start, for example, with 0.5, okay. Then I get 0.4, okay, I'm still in, the sum is still below 1. And then at some point I say, okay, now cut, I have a third parameter, so I need the weights to sum up to 1, and then I simply put it to 0.1. And if I have 0.5 and 0.5 again, I write 0, 0 for the remaining weights. That's how I create this vector of random weights between 0 and 1. Do you have an idea why these portfolios are so extremely inefficient? There is one simple, at least one reason why these portfolios are inefficient. On average. Maybe you can see this from the code. Idea? It's here. What does that mean? Rand 1. Yeah?
You're generating a random number between 0 and 1.
Yeah. All weights are chosen as a random number from the interval 1 to 0, meaning that short selling is prohibited. All weights are non-negative. And if you take a look at the minimum variance portfolio, you have already in the minimum variance portfolio 2 assets that you need to short sell. So let's continue. Why are they so inefficient? Because short selling is not allowed. So the weights do not allow for short sales, and Deutsche Bank and ThyssenKrupp should be... You need short selling for Deutsche Bank. That's more realistic than one would hope for. Then let's turn to optimal portfolios. We have different degrees of risk aversion. You know this. A more risk-averse investor would choose a different portfolio on the edge of the efficient frontier as long as we do not allow for a risk-free investment. So there's no portfolio that is optimal for every investor. We need each investor's risk preferences, that is a utility function. Now let's quickly turn to the utility function here. We're using portfolio return minus 1/50 times the portfolio variance. That's a very simple quadratic utility function with risk aversion. And the goal is now to find an optimal combination of those assets that gives you a portfolio that has an optimal utility for an investor who has this utility function, who has this risk preference. So let's do this. We need sigma, it's the standard return. K is the correlation of return. The objective function is phi is x minus x times mu minus 0.02, that is 1/50, times the sum of x transpose times x and sigma transpose times sigma times the correlation matrix. So this here is the risk preference function, the utility function. And to construct a portfolio, we now require a constraint. We require that the weights again add to 1. Without short sales, we again have portfolio weights that are non-negative. And F-min con needs a starting value. So we'll start with an investment in the first asset with 100%. That's our starting value. The constraints are A is empty, B is empty. A equation is a vector of 1s. All the stock weights add to 1. B equation is 1. Lower bound is 0. And the upper bound, we leave that out, so we have no short selling and the stock weights add up to 1. We do F-min con, use F-min con on phi, and we get XOL and phi val OL. And as you can see, we get this result. Now, we have short selling here, but this is indifferentiable to 0 for MATLAB. By the way, this is also true in statistics. Sometimes in statistics you see coefficient estimates minus 0.0000, and it's statistically insignificant. And when something is statistically insignificant and in this case, these estimates are also insignificantly different from 0 for MATLAB. It doesn't matter whether you have -0 or +0. If it's insignificant, you don't need to care about the sign of the number. And phi val OL is 0.0016. Now, with this, we can calculate the mean return and the standard deviation of the returns of this portfolio that yields the optimal utility. It's not optimal in the sense that it yields the best combination of mu and sigma, but it's optimal in the sense that with this special utility function, you maximize your utility and you get mu and sigma equal to 4.95% and a sigma of 1.close to 6. Yeah?
Can we go back 2 slides, please?
Okay.
So, what do the numbers tell us?
Those are the weights.
The weights,
Yeah.
So,
Meaning
if
you will...
there's 0, what should I do? I should just leave it out?
Yeah.
Or?
You don't buy this asset. And in this case, we know that probably at the 15th or 16th decimal point, there might be a 1, 2, or whatever. So it's close to 0 for MATLAB. When we only use 4 decimal points, it might be that at the 15th or 16th decimal point, it's not equal to 0. But as we are requiring no short selling, you can immediately say this has to be 0, this has to be 0. And this is no surprise. We've seen that ThyssenKrupp and Deutsche Bank, those are the 2 stocks that are that have short selling, that are short sold in the minimum variance portfolio. And if you disallow short selling, if you're not allowed to sell them short, you will definitely not buy them. So the weight will be 0. You will put 61.76% of your money in stock 1. You will not buy stock 2. You will buy stock 3 with 6.76% and so on. Those are the asset weights in the portfolio, and that's your utility. And because your utility doesn't tell you much, you calculate mu and sigma p for this portfolio. Now, the optimal portfolio lies on the preference function phi star. The preference function is a set in the sigma mu plot as different functions result for different values of phi. It's the same idea we are looking at indifference functions, Indifferenzkurven. The higher the indifference curve, the higher the utility we get. And sorting the preference function yields mu pf is equal to phi plus 1 over 50 times the portfolio variance. And inserting the value of the preference function for the optimal stock, we have phi star that was equal to, let's see, 0.0016. If we insert this, we get the preference function, the indifference curve for this utility function. So the optimal portfolio lies on the preference function, and you can show this here. The red curve is the indifference curve for this fixed value. Actually, I think it's plus. Should be plus, yeah. And the optimal portfolio is here. Why is it not a tangent portfolio on the efficient line, on the efficient frontier? Yeah? Yeah, no short selling. So what will happen now? If we allow for short selling, we can move the indifference curve out, and in somewhere here you will get an optimal portfolio on the efficient frontier. So why does the optimal portfolio not lie on the efficient frontier? Again, short selling is banned. This is a theoretical result. However, history has seen many instances in which stock exchange regulators supervisors have banned short selling. The last famous example was during the financial crisis when the SEC and around the world stock exchange supervisors banned short selling on financial stocks. Do you think this is a good thing? Well, research has shown in 2 papers in the JF and the RFS by Beber and Pagano, for example, and also one paper by Böhmer et al. It doesn't really lead to better stock returns. It doesn't prevent financial crisis. However, it wreaks havoc on market liquidity. If you ban short selling, the result will be that liquidity dries up dramatically. And thus, short selling bans have high collateral damage. They come with high collateral damage to market microstructure. Then, if you allow short selling, constraint of non-negativity is lifted. We do the same without this constraint of short selling, and you see we are now short selling stock 2, 4, and 6. We get a different phi, a different utility value, and if we now plot this, the result will be that let me see, let's stay here. Okay, was here, not here, but this is where we stay here. This is now the optimal portfolio on the efficient frontier. If we have no short selling constraint, we'll get a point on the efficient frontier for this particular investor. If we were to use a different utility function, what would happen? The utility function could look like this. Then you would see that suddenly, well plotted, suddenly this portfolio would be optimal for investor 2. And then you could include additional constraints. You could also include a risk-free investment, and you would see the result somewhere else. So if short sales are allowed, the optimal portfolio will lie on the efficient frontier. Thus, the optimal portfolio is the tangent point of the indifference curve and the efficient frontier. Technically speaking, you can see that for this investor, a ban on short selling is a market friction, and it's a problem for market efficiency. The investor is not allowed to reach his or her optimal portfolio because it cannot include additional stocks via short selling. So the result will be market frictions and inefficiencies, and this has also been analyzed empirically by at least 2 papers in the literature. Okay, do you have any questions? You should be able to download the data from the website, and I think I also uploaded, maybe not for this, but you can simply copy the code from the slides and then insert it into MATLAB, and you can run the optimization on your own, maybe play a little bit around with the constraints, include some additional constraints, and see what happens. Okay, so if you have no further questions, thank you very much for your attention, and see you next week. Thank you.